In this video, we'll run a multiple logistic regression with one categorical independent variable and one continuous independent variable. We're using the Youth Cohort Study of England and Wales 2004 to 2007 Cohort 12 dataset. This dataset is available for free download from the UK Data Service website. Let's say you want to answer the following question. What are the odds that a young person will not be enrolled in full-time education after secondary school, taking Year 11 placement satisfaction and total GCSE score into consideration? Our variable of interest is S2Q10, a measure of enrollment in full-time education in Sweep 2 of the Youth Cohort Study. It's a binary categorical variable, meaning it has two categories. This means we can model it using logistic regression, which requires a binary variable as the outcome or dependent variable. Because respondent placement satisfaction may be informed by total GCSE score, which in turn could influence enrollment in full-time education, we can fit a multiple logistic regression model using S2Q10, or full-time educational enrollment, as the dependent variable, and both S1Q4, or placement satisfaction, and S1 GCSE points new, or total GCSE score, as the independent variables. We are running a multiple logistic regression because it will allow us to control for the influence of each of the independent variables on our dependent variable. To run the logistic regression, go to Analyze, Regression, and Binary Logistic. First, we will find our dependent variable, S2Q10, and move it to the dependent text bar. Then we'll find our first independent variable, S1Q4, and move that to the covariates text box. Now S1Q4 is a categorical variable, so we'll need to tell SPSS that it's categorical. Go up to the categorical button in the upper right, and just move S1Q4 from the covariates text box on the left to the categorical covariates text box on the right. Click Continue. And then finally we'll find S1 GCSE points new, here we are, and move that variable from the variable list to the covariates box as well, because it is also an independent variable. However, it's not categorical, it's continuous, so that's all we need to do for S1 GCSE points new. Because we may want to be able to generalize our results to the whole of the population from which this survey data was taken, in this case to all of England, we should also calculate confidence intervals. So we'll click Options, and under Statistics and Plots, we'll select CI, confidence interval, for XB, and it's already set at 95%, so we can just click Continue, and then OK to run the logistic regression. In the Case Processing Summary output table, you can see how many cases were included in the analysis, how many cases were excluded or coded as missing, and how many cases we have in total in our survey. The Case Processing Summary table tells us that we have 14,003 cases total in our survey. In this dataset, in the dependent variable S2Q10, the category Yes is coded as 1, and the category No is coded as 2. An answer of No, therefore, has been arbitrarily given a larger numeric code, as 2 is greater than 1. In logistic regression and SPSS, the variable category coded with the larger number, in this case No, becomes the event for which our regression will predict the odds. In other words, because the outcome No is coded as 2 in the dataset, the logistic regression will predict the odds of a respondent answering no to the question of whether or not they were enrolled in full-time education. Because we're now predicting the odds of a respondent answering no, this answer becomes the success in our model, or 1. An answer of yes is a failure, or 0. This is reflected in the dependent variable encoding table. This shows us that the original values of yes and no are coded as 0 and 1 in this analysis. The categorical variables codings table shows us the frequencies of respondent satisfaction with their placement in education, work, or training. In addition, it also tells us that these three categories in our categorical variable S1Q4 have been recoded in our logistic regression as dummy variables. In logistic regression, just as in linear regression, we are comparing groups to each other. In order to make a comparison, one group has to be omitted from the comparison to serve as the baseline. In our logistic regression, no has been selected as the baseline, or constant dummy variable, to which we will compare the predictions for yes and to some extent. Therefore, no won't be included in our model. You can see this in the table, because it isn't coded with 1 in any case. This is because it is the baseline comparison category and has not been added to the model. The output tables in Block 0 beginning block show the full-time education enrollment predictions before the additions of our independent variables S1 GCSE points new and S1 Q4 into the model. Block 0 shows the odds of a respondent not being enrolled in full-time education without the influence of GCSE score and placement satisfaction. In the variables in the equation table, we can see the odds of not being enrolled in full-time education. These odds ratios are presented as the XB output in this table. Here we see that without the addition of GCSE score or placement satisfaction, the odds that a respondent would not be enrolled in full-time education are 0.235 the odds that a respondent would be enrolled in full-time education. In the variables not in the equation table, we see the predicted significance for the variables S1 GCSE points new and S1 Q4. If p is less than 0.05, this table predicts that GCSE score and placement satisfaction will be significant, and that the additions of these second variables will improve the fit of the model. We can see that the predicted p-values for S1 GCSE points new and S1 Q4 are 0.000, meaning that they are all predicted to be significant. The Block 1 output tables shows us the relationship between our dependent variable, S2Q10, and our two independent variables, S1 GCSE points new and S1 Q4. The omnibus test of model coefficients output table shows the results of a chi-square test to determine whether or not placement satisfaction has a statistically significant relationship with enrollment in full-time education. The chi-square here has produced a value of p is equal to 0.000, making our placement satisfaction model significant. We can use the Cox and Snell R-squared statistic calculated in the model summary output table to gauge how much of the variation in full-time enrollment is explained by this model. In this example, the R-squared is 0.192. This shows us that 19.2% of the variation in enrollment in full-time education is explained by Sweep 1 placement satisfaction and total GCSE score in Year 11. We calculated this by just multiplying 0.192 by 100. This suggests that despite our inclusion of two independent variables in this model, other factors are influencing a respondent's enrollment in full-time education. Finally, the variables in the equation table shows us the significance levels for each of the variables we've included in our model. We can see that the p-values for S1 GCSE points new and both of the dummy variables in S1 Q4 are 0.000, meaning that for both of the variables we've included in this model have statistically significant influence on respondent enrollment in full-time education. Remember that in this model, in S1 Q4, no was selected as our baseline comparison dummy variable. Because S1 Q4 with a p-value of 0.000 is a significant predictor of the odds of enrollment in full-time education, we can use the odds ratio information provided for us in the XB column. We can say that a respondent who was happy with her placement in Sweep 1 has odds of not being enrolled in full-time education that are 0.232 the odds of someone who was unhappy with their placement. This means that those who are happy with their placements are more likely than those who are unhappy to be enrolled in full-time education. This is because an odds ratio of less than 1 means that the odds of an event occurring are lower in that category than the odds of the event occurring in the baseline comparison variable. Because an odds ratio of 0.232 is less than 1, this means that the odds of not being enrolled in full-time education are lower for those who were happy with their placements than for those who were not. We can see in the XB column for S1 GCSE points new that the odds ratio for GCSE score is 0.991. Because S1 GCSE points new is a continuous variable, we can say that with every point increase in GCSE score, the odds of not being enrolled in full-time education after secondary school are multiplied by 0.991. Because 0.991 is less than 1, any odds being multiplied by 0.991 will necessarily decrease. Therefore, as GCSE score increases, the odds of not being enrolled in full-time education decrease. Young people with higher GCSE scores are more likely to be enrolled in full-time education after secondary school.